Record. There we go. Yeah, it is recording. Thanks for reminding me. That was really nice of you. I think we should give people another couple of minutes, yeah? Or are you still logged into the GoToMeeting?
I am.
Ah, okay. So I'll wait another couple of minutes and then I'll start.
Yeah. There's nobody left in GoToMeeting, so feel free to start here.
Awesome. All right, great. Cool. So once again, for the people who just joined, apologies for the confusion with the GoToMeeting versus Zoom. We had a little bit of a technical issue, but we're now ready to start. So my name is Michele Pazena. I head up the Dimensions Data Solutions team. Essentially, I spend a lot of time trying to let people access the Dimensions data as raw data or in some form, as pure data. And so today I'll be talking about the Dimensions API, and in particular the Dimensions search language. It's a language we created ourselves in order to simplify access to Dimensions data using the APIs. So for those of you who are not familiar with Dimensions, I believe probably most of you are already, but anyways, I'll just say that one of the key things about Dimensions is that it combines different research documents, different document types within a single platform. So we have a lot of information about publications, of course, but we also have grants, patents, clinical trials, policy documents, data sets, and more documents being added all the time. And really the unique feature about Dimensions is that we spend a lot of time trying to interlink all of these different data sources. Can I very quickly ask you guys to mute yourself? I don't know if I can. Oh, I can actually do it from here. There we go. Done. Lovely. Right. So yeah, that's the unique thing about Dimensions. We have lots and lots of links essentially across all of these different data types. So by using the web interface, by searching using the web interface, of course, you can take advantage of all of these links, but really these links, they become available. I mean, you can take advantage of these links more by using raw data access in some form. So this is a little bit of an overview of the products you can access using Dimensions. We have the web app on the left hand side that, of course, allows for search and discovery. It tries to support the most common analytical use cases that we know people in different research areas or people in different disciplines are interested in. Of course, it's a user interface, so the number of things you can support using it by it are always limited. And so that's the reason why we also offer access to the raw data behind Dimensions in different formats, because you may have some ad hoc way of accessing the data or making use of them in order to address your specific use case that the web app, the user interface, doesn't support. And so you want to get to the raw data, to the data themselves, so that you can build your own solution on top of it. And there's three ways of getting to the data. The first one is the API. That's what I'm talking about today. The API is geared a little bit more towards ad hoc analysis, where you're looking at one single data type at a time. So the API allows to perform full text search, just like you do with the web application. And it's primarily used, and we'll see more about that. It's primarily used when you're essentially trying to build some sort of integration with another tool. So for example, you want to pull data from dimensions regularly because this data needs to feed into some other system. It could be your own research administration system, or maybe it could be a dashboard that you're building and you need to get data from dimensions. And so the API is probably the most cost-effective way to pull data from dimensions into your platform. The other product we have is called Google BigQuery. Essentially, that's kind of a relational database in the cloud, hosted by Google, that contains all the data we have in dimension. So this other solution is much more geared towards very large scale analysis. So this kind of analysis, for example, involves touching millions, if not like hundreds of millions of data points. You may want, for example, to measure impact of publications across different countries or different organizations or across a very large time frame, and you want to do that quickly. So the Google BigQuery solution allows for this sort of analysis to happen very, very quickly. You can do it in seconds. Um, but of course, if you need to run the same analysis over and over, every hour, every minute, it's probably not the best place to do it because there are different costs involved. So that's what Google BigQuery is primarily targeting. So very large scale analysis for kind of one-off investigations or analytics tasks. And finally, we have the bulk data deliveries. With the bulk data deliveries, we essentially give you access to all the raw data behind dimensions as JSON, essentially in the same data format that we use to store the data in our own databases. So this fourth solution, of course, will take a lot longer to you have to digest the data yourself. So you need to set up some sort of data pipeline to put the data into a system that you own. It could be a database or, well, a relational database or some other sort of database that can handle, the large amount of data we have in dimensions. And then after you have done that, you can then process it. So the bulk data is probably much more geared towards teams that already have quite a solid, data engineering capability, and they want to integrate a new data source within their data lake or data landscape. So these are the four main, I would say, ways to access dimensions. And so today we'll be looking at the API in particular. So what are the use cases people have when they come to the API? So they may have some queries that would be difficult or impossible to do using the web application. So for example, citation analysis, queries where, for example, you want to take the results of the first query and pass them on to the results of another query and to do that over and over. So citation analysis is probably, very, very, very common use case. Second reason why people use essentially APIs is because you want to automate this process. So you may have a bunch of keywords you want to run queries for over and over, or the same citation analysis query you want to run it every day or every week or every hour. And that's because you're trying to build some sort of report or a dashboard using this data. So that sort of automation can be done using the API. And finally, people come to the API because they want to get more than the 50,000 records that you can export using the web application. So with the API, it's easy to pull millions of records a day or something like that, simply because it's so easy to slice and dice the data in multiple ways that you can set up a script or an extraction mechanism where you essentially pull data by year or by week, and you can easily export a lot of data so that you can then process it offline. So that's the third reason why people come to the API in a nutshell. We have two main API products. The Analytics API is the one I'll be showing you today. That's also the most advanced API we have. It contains all the cutting edge features we develop. We make releases quite frequently, every few weeks. The API is throttled at 30 queries per minute, meaning that you can run a query every 2 seconds. And the main use case here is for analysts or data scientists who have sophisticated queries for dimensions, and they want to pull the data the raw data from it using the DSL. Um, Now, the second API product is primarily for quiz systems, essentially for systems using um, in research and academic settings to monitor, to keep track um, of research outputs or research activities. So this second API has a bit more focus on stability and reliability. So we don't update it as frequently as the analytics API. So maybe we update it 2 or 3 times a year. We really want to make sure it never breaks, because the main purpose here is to use the API to integrate with some other system, with some other proprietary or internal system an organization has. It's the same amount of throttling, so 30 queries per minute, meaning that if you're building an integration with this API, you need to essentially make sure you don't query it too often. And the use case, as I mentioned, is the integration with quiz or RIM systems, which is another type of research administration systems. Right. What both of these APIs have in common is that they use the dimension search language. This is a powerful query language that we developed around a very simple syntax. It looks a little bit like SQL for those of you who have some knowledge of relational databases, but it's actually way simpler than SQL. And the reason why we built this language is that we wanted to essentially make it easier also for analysts or workers who do understand the research domain well, but they may not have such a strong background in computer science. So we wanted to make sure that also these people can become productive with this search language, with the API. And so the language is, of course, based around English keywords. There's always 2 phrases, a search and a return statement. In this case, for example, I'm searching for publications, but you could be searching for any of the other major content types we have within Dimension. So, grants, patents, clinical trials, and so on. So you can search and return objects. Of course, that doesn't do anything too interesting. So normally you would put in a keywords to search for in the full text of the documents. You can add some filters. So for example, the years you want to search in, or maybe the academic journals you want to search in, and so on. You can even specify exactly what objects to return. So you don't necessarily have to search for publications and return publications. You may be returning researchers or journals. So that's a little bit like a group by operation or a faceting operation, because you will be returning only those objects related to the publications you have been searching for. And we'll see specific examples of this in a minute. Now, another section of the dimension search language that I will not be talking about today, but you can, but I still wanted to mention it, is this area called special functions. These functions, they don't let you search for the documents we have in dimensions directly, but they kind of take advantage of the documents in different ways. So for example, over the years, we have built a very sophisticated machine learning algorithm for matching raw affiliation strings to grid identifiers. So grid, the research institutions database, is the main essentially set of organizations identifiers we use in Dimensions. It's totally open source. You can download it. It's actually, I think the license is 0, so you can even reuse it. Of course, when we get information about affiliations we find in publications and other documents, we don't necessarily find a grid ID associated to these. So we developed a process to essentially match automatically, for matching automatically an affiliation string to a grid identifier. So by using the extract affiliation function, you can actually take advantage of that same feature we use internally. So for example, a classic use case here, you may have a whole bunch of internal documents containing affiliations data that you want to align to the grid identifier system. And the reason you want to do that is because then you can use these links in order to take advantage of the rest of the information you find in dimensions. And so you would use this function to do that. Another one we have allows you to extract concepts from text. These concepts are kind of keywords, um, weighted keywords that we also use in dimensions. And of course, they have been normalized according to the full dimensions corpus. So you could use this function, for example, for some quick and dirty topic analysis, or as a building block to essentially extract some keywords that then you want to process further in order to create some sort of natural language pipeline, or some more sophisticated topic-based analysis. Um, the third function, and there's actually more than three, but I just mentioned three today. The third function I have here is the classify one. In this case, you can still pass some text, more. Normally, it would be a title or an abstract, and you can specify what classification system you want to use. Here we have the FOR, the Fields of Research Codes classification. That's one of the many classification systems we have in dimensions. And so this function will then spit out a taxon, an item from the FOR taxonomy that matches your text. And once again, what's happening in the background is that the entire dimensions corpus is being used in order to make sense of that text and attach it to a specific item in the taxonomy. All right, there's a lot to be said about the dimension search language. The best place to find out information about it is the online documentation at docs-dimensions.ai/DSL. Documentation has a number of different sections. After the getting started and the tour sections, there's you can dig into it by looking at the query syntax. You'll find everything you need to know in terms of how you want to search, how you can do full text or field searching, or specific topics such as searching for researchers or searching using concepts. And by the way, the hands-on session I'll be doing in a little while will cover exactly this section here, the query syntax. So I'll be going through all of these different topics in details. Now, going through the other parts of the documentation, we have the functions section. So the functions are the ones I just mentioned, like classify, extract affiliations, and so on. There's another section about experts identification. This is a feature we released quite recently, a few months ago. It's kind of a workflow where you can use two different functions here in order to go from raw text to a list of researchers that Dimensions knows about that are relevant to that text. And so we call this workflow expert identification, and it's a pretty powerful one because it can be used in different contexts. You can essentially find experts for some specific topics, or you can even try to find reviewers. So there's a number of aspects that can be a number of use cases that can be leveraged using this workflow. Finally, the other very important section in the documentation here is the data sources one. So here you would find for each of the main content types we have in Dimensions, details about what fields are available, what are the data types for those fields, and how you can use them in the Dimension search language. So here on the landing page of the data sources, there are also some nice data diagrams to show you what are the links between the different data types we have. And for example, if I click on publications, you will see here a long list of all the fields available for publications that, pretty much it would match one-to-one with the fields you see in the web application. So if you're essentially doing a search using the website, the Dimension website, you should be able to do exactly the same search using the API as well. Right, we have a whole section here down here about example queries and results you can play with. And finally, a few other sections about on how to get started with the API, how to get access, Of course, that really depends on what system you're using to access the API. And in particular, if you're not really a developer and you want to have a kind of quick, way to get productive with the API, we also have a Google Sheets add-on, which is completely free. You can simply install it in via Google Sheets, and that allows you to run queries directly from a sheet and to get the results in tabular formats within Google Sheets, meaning that then you can, take advantage of your spreadsheet skills in order to analyze the data, to build visualizations, or to pivot on the data and essentially um, generate some insights from the dimensions data. So I'm going to go back to the slides now. Right. So we talked about the online documentation. There's another very, very important resource about the API if you're keen on learning about it and becoming productive with it. This is called the API Lab. This is a collection of open source Jupyter notebooks showing you how to not just how to use the API, but how to essentially take advantage of the API in combination with Python in order to carry out some common scholarly analytics tasks. So for example, we have notebooks showing you how to calculate the H index of a researcher using dimensions data. We got notebooks showing how to analyze the collaboration patterns, both at the international level, national, or looking just at industry collaborations. And all of this, of course, cannot happen just with the API. There will be steps where there are API calls, some data is retrieved, some other steps where we use Python and other visualization libraries to make sense of this data, and then maybe feed these results into a further step that does something else. So there are a lot of notebooks in the API lab you can take a look at. Um, Actually, the demo session I'll be giving you is actually one of the notebooks you see here. Hold on, I already opened that earlier. Let me close it down so we can start from scratch. You can see how that works. Um, so we have a whole section about on how to get started with the API, introductions about the different features, and then we got different sections depending on the content type you are interested in. So for example, for publications, there's a section about topic modeling analysis. I'm just going to open this up here quickly. This is an HTML page, essentially a rendering of the notebook, but you can download all of this and run it locally on your computer and essentially customize the search queries, customize some of the parameters being used so that you make it more relevant for you, and rerun the whole thing. In this case, for example, I think we are running a query on um, I believe in publications in social and social sciences and philosophy for a specific organization, and we're extracting concepts in order to draw a very quick and dirty topic map representing what are the key areas this organization is working on. And right, so there's plenty of notebooks here you can play with, customize, and trying to become productive with. So API Lab, very, very useful resource. So how do you access the API? So the quickest way is probably via dimensions. So if you have dimensions access, I'll show you how you do that. You can simply go to workflow. I'm logged in here, so I can see this menu, workflow, API, and you end up on a page like this that allows you to very, very quickly run API queries. So for example, I can simply say search publications, return, say research orgs. I'm going to say limit 10, show me the top 10. So in this case, I'm faceting because I'm saying search publications, but don't return publication records. Just show me, so send me back the top research organizations linked to these publications. So effectively, what I'm doing here, I'm generating a list of the most prolific research organizations we know about in Dimensions. So the data coming back, they have a structured format, which is called JSON. You get some statistics at the top, some information about the API version. And then down here in this section called titled Research Orgs, I get a list of the top 10 research organizations linked to publications in Dimensions. So I'm going to open up the first one. As you can see, it's Tokyo. I get a count. So that's the total number of publications Dimension knows about coming from Tokyo University. So together with the name of the organization, there's also other information. All of this can be fully customized, but that gives you an idea what you can get back. So the second one is Harvard. So I'm gonna keep scrolling down. Toronto University, Michigan University, and so on. So this is essentially the web app access for the API. Of course, you're probably thinking, so what next? Yeah, this is a little bit of a dead end. This is a quick way for trying out a query and see what the results come back. But really, if you want to um, be more efficient, or to build some real world analysis um, of using dimensions data, that's not how you would do it. So so you have two solutions in that case. The first one would be either using a third-party software that have some sort of data connection. It could be something like a BI software like Tableau, visualization, or even Google Sheets. Essentially, some software that knows how to interrogate a REST API, an external API, and pull the data into the system, and then you would do something else with the data. So that's one way. And the second way is by using a programming language. So this is by far the most flexible way of essentially working with APIs, because once you use a programming language, you can essentially manipulate the data in any way you want, and you can then maybe pass it on to other visualization libraries or other statistical analysis libraries that you may be familiar with. So we have people using the API using all sorts of languages. Internally at Digital Science and Dimensions, we like Python a lot. We've been working with Python a lot, and so we actually have developed a library called Dimkly for Python that makes it easier to access the API. You don't have to use Python, of course. For example, there's a couple of other libraries that have been contributed by external users in R, which is another very common language for statistical analysis. So you have a whole bunch of options if you want to use different languages with the API. I did mention the Google Sheets data connector. That's a very quick way to get started. Dimkly or Dimkly, the API Python client, as I mentioned, this is also it's open source, is freely available online. You can download it if you know how to work with Python and Python libraries. It can really speed up the process of logging in and out of the API, of launching queries, of trying things out, of turning results from the JSON format we saw earlier into data frames, into a tabular format, or even into Google Sheets, into other formats in general. So Dimkly library, it's a very useful resource if you're Python based. Right, so that was a very quick tour of I'm aware of the fact that there was a lot of content, but hopefully many of you were already partially familiar with some of it. So what I'm going to do now is take one of the notebooks. I'm here on the API Lab website. I'm going to take specifically this notebook here. Let me close down these other tabs. All right. This is called Exploring this Dimensional Search Language, a deep dive. And essentially, this notebook goes through, I would say, pretty much all the main sections of the dimension search language. So it's a very, it can be a bit, of course, we're not really doing any real world scholarly analysis, something that you can probably use in other contexts, but this is really trying to show off all the things that the dimensions language can do. So it's a nice place to start if you want to become a dimension search language expert. So what I'm going to do, I'm going to run this notebook online. As you can see, all of these notebooks here, they have two buttons at the top. One says open in Collab and the other one says download from GitHub. So if you download it, you can run it locally within your own Jupyter environment. If you don't have that, or if you're in a rush, you can run this, completely online. This can happen thanks to a product from Google called Google Collab, which is essentially a Jupyter environment which is fully hosted online. So what's happening here is that a version of that notebook opened up in the cloud. You can think of it a bit as a Google document in a way, but it's a Google document that mixes up text and code. So I can run these code cells and they will produce something. All of this is happening in the cloud, so you don't have to have anything specific installed on your computer. So this is a very, very handy way to perform some analysis without having to maintain a development environment on your computer, which is sometimes, it can be very time consuming. So I've now opened this notebook and the way you interact with the notebook is by hitting these little play buttons here. So when I hit play, the very first time I do it, essentially, Google simply tells me this isn't something you worked on before. It's not your notebook. Make sure you run it. And once you run it, essentially, this Python instructions will be run in the cloud. And the very first cell of each of these notebooks in the API lab will normally ask you to log in, right? So here it's asking me for an API key. So I'm going to go back to dimensions here and look for my API key. I think you find that under your account. I go to my account. Here we go. So that's my API key. I'm going to copy that. I'm going to put that there. There you go. So now I'm logged into the API. I can actually start running queries. So the other thing that is happening here is that I'm loading up the Dinkly library I mentioned before. And that's because Dinkly library contains a number of really little tools that make it easier to interact with the API. One of these tools, this is called a magic command. Essentially what it is a bit like a shortcut. I can simply put in this command here called DSL-df. It stands for, DSL is dimension search language, df is data frame. It means it's running a query to the DSL and the results coming back are turned into a data frame. A data frame, for those of you who do not know what that is, it's a term coming from another Python library called pandas. And you can think of it a bit like, Excel for Python, spreadsheets for Python. So it turns a different data structure into a tabular format. And then you can use that tabular format to perform other operations. So if I run this cell again, so essentially what I'm saying is, search grants and return grants limit 5. Very stupid query, it doesn't do much. It simply takes the top 5 records in the grants database. So if I remove the df bit there, I simply say DSL, search grants, return grants. As you can see, I don't see the table anymore. And I simply say an object coming back called the Inkley dataset object. And let's say we save this object now to a variable called test. And if we look at test, we can say test.json. And within that object, you see we have the raw JSON data coming back from the API. This is the same exact data format I was showing you earlier when I was searching using the Dimensions web app. So that's how you get to the JSON data if that's what you're interested in. So I'm gonna get rid of that because actually today we won't be interested in the JSON data per se. We just want to see what the search language looks like and what you can do with it. Right. So every search statement always contains a search and a return part. So as I showed you earlier, you can then start adding more constraints for the search. So in this case, I'm searching for grants, and I'm also putting in a filter. So I'm looking for grants matching the keyword lung cancer, where the active year is 2000. Right. So that's another very, very simple query. Um, I think we've seen already that you can decide what result type you want to get from a search. So I can search grants and return grants. And then, of course, sends me back a list of records, a list of grant records. But I don't necessarily have to do that. I can essentially facet on other objects that are related to grants. So for example, as you can see here, I have title for grants, I've got funders, funding orgs, start date, language, years. So for example, I think something you can do here, I can say search grants and return start year, right? So you can think of this a bit like a group by operation. So for those of you who have some knowledge of SQL. So what I'm getting here essentially a list of years, and by default, I'm aggregating the total number of, well, the dimension search language aggregates the total number of grants for that year, and it sorts the results using this total number. So here I'm searching for grants on this topic, laryngectomy, and I get back the years. I can say return funders, and what I'm getting back is a list of organizations instead of getting a list of grants. Now, the nice thing about the DSL is that if you make an error, like in this case, the DSL tries to help, as much as it can. So essentially, system now is telling me funders, doesn't mean anything here. These are the facets you can use. And as you can see, there's a whole bunch of facets, things you can pivot on to run your search. So another probably very useful one is categories. I've picked category now. These are SDG categories. Well, probably more useful to use the field of research codes. So what I'm getting here then is a breakdown of grants matching this topic, of course, using these field of research codes. And for each one of these, I get a count that tells me how many grants I have in that specific area. Right. So you'd probably be wondering, so what are the facets I have available? How do I find out? Well, obviously, the best place to find out about this stuff is the documentation online. So here I'm going to the grants homepage. We can see all of the fields available for grants. And whenever one of these fields can be used to facet, to group by, we see a tick in that column. So this is the place to find out about what features are available for each of the content types. It's not the only way to do it, though. The DSL dimension search language essentially has a functionality called Metadata Api. What that means is that you can query for the language, query and obtain information about the language itself. There's actually a shortcut you can use for it, another magic command, which is called DSL docs. So if I say DSL docs grants, I think, yeah, I need to do it like that. DSL docs grants, what I'm getting back here is not information about the records we have in dimensions, but this is actually information about the API language itself. So I get here a long list of fields, essentially the same information you would see in the documentation online. You can actually query for it. Yeah. So that could be a nice feature if you're trying to automate some of this stuff, or it's also very handy if you want to find out about the API language without having to leave your Jupyter environment. Right. So let's move on to the next topic, and this is probably one of the most important topics with the dimension search language, which is full text search. So full text search, in essence, is about finding instances of a keyword in documents. So the way it works is that you always specify what search index you want to search in, and then you specify what are the keywords you want to search for, right? Just like that. So in this case, I'm searching in the full data, meaning across the full document indexing we have for the specific topic called the moon landing for these keywords. Right. So, oh, what am I doing here? So it's important to point out that there are a number of search indices, essentially of areas of the documents we have indexed, and you can specify exactly then where you want to search. So once again, to find out which are the search indices you have, you should go to the documentation here. So here I'm looking at publications. I'm going to click on search indices. And so, for example, for publications, these are all the different specific areas you can dig into with a full text search. So I can look into the titles only, titles and abstracts. And by the way, when you use title and abstracts, there's a bunch of other identifiers included. So you can put in a DOI and you would match it. We have an index called full data exact. In this case, we're not normalizing text of documents. So for example, if you're looking for scientific terminology or like gene names or chemical compounds, this is the index you want to use. Then we have the full data index that contains essentially anything any text we find in documents. And this index is normalized. So for example, all terms are lowercase. We sometimes, synonyms get added or plurals get removed and things like that. So this is, full data is probably one of the indices you'll be using the most when you do searches. And then finally, we have other two, one for concepts and one for authors. So concepts are kind of, weighted keywords that we extract from documents. So it's a bit of an alternative to a full text search because concepts essentially they contains only the keywords that, based on the knowledge dimensions has about that publication are the most relevant for that object. So in many situations, searching in concepts can give you results that are more relevant to your topics. And finally, we have an index called authors um, that contains a normalized version of the author name. So for searching in authors, you always have to put in a name and a surname, and it essentially enhances the precision of your searches when you're looking for author names. We can look at an example of that in here. Right. So just like before, you can access information about the indices using this Meta API directly. So that's the query, describe schema, and then I'm saying, give me only the search fields for grants in sources. So in the case of grants, these are the search fields you can search for. So here I'm searching for grants and I'm specifying match only full data for these keywords, graphene and computer and iron. So I want all these keywords to be present in the results. And I get 12 results in total. And of course, if I say title only, I probably get 0 results here because, the chances of these keywords to be appearing together in a title are not many, but let me relax that query there and say only computer and graphene, and I get 6. So if now I go back to full data, I'll probably get many more. So 539. Right. This is an example of how searching in the authors field for publication works. So search publications in authors for this specific name. So the author's index essentially contains different variations of this name. It could be name and surname, or maybe surname, comma, name, or names, initials, first name, initials plus a surname. So it's an optimized index for these sort of searches where you know a person's name and you want to try to find it. You don't have to do it this way. You can even try to have a fuzzy search. Of course, you would get back, much more noise, but in some cases, that's what you want. But if you do know for a fact, what is the name of a person, this is the more precise way of looking that person up. Right. So when you do a keyword search, you always have these 4 keywords saying essentially what it is that you are searching for. If you want to do an exact search, you need to put quotes in your search. And what that means is that you need to add an extra slash to make sure that the quotes are escaped. Yeah. Because of course I have quotes outside my keyword search text. Also I have quotes inside, so I need to make sure the inside quotes are not treated as the outside one. And you do that by escaping. So in this case, I'm matching only publications that have machine learning in title and abstract. Machine learning as a single word. There's a whole bunch of other characters that need to be escaped. If you run into those issues, the documentation will tell you everything about it. But maybe it's important to point out that you have a whole bunch of Boolean operators that can be used for in a search. So you can use brackets, you can use and, not, and nor operators, so you can go wild with very complicated search phrases. So in this case, for example, let me change that to a double ampersand so I can put this in multiple lines. Say search publications for either those or concentration, and another constraint is that the documents, they need to have the Africa keyword, but not the malaria keyword. So plus and minus are a bit like a shortcut of not and must. So essentially here I'm getting only documents where Africa as a keyword appears, malaria does not appear, and either those and concentration appear. Right? So of course, you'll probably be spending time figuring out what is the best sequence or combination of keyword constraints to define your corpus. And you can do that iteratively by using a notebook, just like I'm doing now, or even by using the interface in some cases. That's another workflow people use. You use the UI to do some searches to understand exactly what is the best way to identify your corpus, and then you may be going back to the API in order to pull the data, to pull all the data you get from that search. Of course, this search strings, they can be pretty complicated. This is, for example, the keyword search string for the COVID-19 publications that are freely available as part of the effort we have made, with the Dimensions team to make available all the COVID-19 related content online. So you can go to covid19.dimensions.ai to see that. So in order to generate this page, we essentially use a keyword search, which is exactly the one we have here. So in this case, as you can see, the keyword search contains a whole bunch of quotes inside. So what I'm doing in order to run it, I first write it out like that, something that you can do by copy pasting the query from the web application. And then I essentially run this little function called DSL escape on the string, and that automatically escapes all the quotes. Yeah, so it's kind of a utility function you would use in these cases because it could be quicker simply to copy paste a query from the web app to here. So we get back this object here. If we want to see the data frame, I can simply say as data frame, and the results coming back are now in a table. All right. In keyword searches, you can also use wildcards. The main two wildcards we have is the question mark and the star. So a star matches any number of characters, and question mark instead matches only one character. Yeah. So in this case, I'm searching for Italy question mark that will match Italy, but not Italian. Down here instead with the IT star, it would match both, both Italy and Italian. The other really nice feature, which is used a lot, is this proximity searches. These are expressed using the tilde operator. Essentially, what I'm saying here, I'm saying search for formal model, and then I say tilde 10. What that means is that these two words have to appear in the results, but they do not necessarily have to appear one next to each other. They can be up to 10 words apart. That's essentially what it is. So this is actually a powerful mechanism once you have a combination of words that really define your subject area well. But you want to make sure that you capture also cases where these words are using combination of other modifiers. Yeah. So for example, down here, I'm looking for digital humanities papers and ontology. But digital humanities, sometimes they can have some other modifier words in between, and I want to make sure I capture those cases as well. All right, so I think that's all in terms of full text search. The next topic is field searching. So the difference between full text search and field searching is that field searching looks at fields that are already structured in dimensions. With full text search, you essentially scan through the text of a document, the text that we have indexed in the database. With field searching, you specify a single field we have, and you search only within that field. So in order to look at the fields available, you either go to the documentation, or in this case, I'm using this DSL docs helper method. This is the list of fields we have in dimensions for publications. Of course, there's a lot of them. And the syntax to look into these fields is simply where. So you use this keyword here, where, and you say where field name equal some value. So in this case here, I'm searching for publications where the type is book, right? If you do not know in advance what types are available, remember you can always facet on this field. So I can simply say search publications, return types. Actually, it's not types, it's type. Let's try that. There you go. So that gives you right away a breakdown of what content types are available in publications. So of course, the vast majority of these things are articles, and have chapters, proceedings, and so on. So now that I know what types are available, I can, for example, say where type equal monograph. And here I get the top 5 monograph articles in there. And of course, you can combine field search and full text search in order to get to the data you want. Right. So let me see. What's next? In some cases, especially when you're dealing with years, you want to do a field search where you say, find me stuff in this year and in this year and in this year. And if you have, a range of 10 years, it may become, very, your query may get really, really long. So there's a nice shortcut here. You can say in and pass a list of values in square brackets. So this is the equivalent of essentially spelling out each single year using a field equal value syntax. So That's the in shortcut. You can use the in shortcut not just with years, but with anything else that essentially can accept a list of objects. So in this case here, I'm looking up grants based on this keyword, and I'm extracting grants where the name of the research organization linked to grants is in this list, right? So that also will work. Now. There are a few fields that allow also counting on them. You should look at the documentation to know exactly which ones they are. But in this case, for example, I'm counting the number of research organizations linked to a specific document. So I'm saying, give me publications matching this topic that have at least 5 research organizations. Essentially, these are papers where there are 5 different organizations essentially collaborating on the research. And this is actually a pretty powerful mechanism to look at collaboration patterns, for example, because I could, I don't know, specify a great organization and say, find me publications from, I don't know, UCL London, where there are more than 10 collaborators. It's a quick way to essentially look at the collaboration patterns for, well, with respect to a corpus of some kind. So I can actually pull it up. There are, yeah, so you can see there are papers where there are more than 50 collaborators. There are articles where you can have actually hundreds of different authors, if not thousands. So this kind of count operators that will make it very quick, very simple to extract that sort of information. You can also count researchers. So that's another pretty handy operation if you want to look at how researchers collaborate, and so on. Right. Oh, here's the example I was talking about here, actually. So this query here essentially says search publications where I have at least more than one researcher, and there is at least more than one country. And essentially, this gives me the number of, this gives me publications where there is international collaboration. And so if you take it like that, this query is probably not too useful. But the moment I mean, as soon as I put in another constraint, for example, I say, and research org equal, I need to put in a grid ID. I've got one here. Always Andy, I think that's Oxford. And I'm gonna return not funders, but years. So years is not right. It has to be year. It's not research org, but it's actually, research orgs. So, all right. So this tells me essentially the number of publications with international collaborations from Oxford by year. Yeah. And just by the look of it, looks like, the trend, this is always going up. But, in some other cases, it might not be exactly like that. So this is just to point out, this simple query here can already, produce some pretty useful insights by using a combination of count and other filters. All right, so let's see.
I'm sorry to interrupt.
Feature
question.
Yes, please.
Chat.
Yes.
Is there a way to address the large number of authors on a physics paper that seems to break the structure when I export it, and it kind of breaks it across multiple rows?
Yeah. So can you expand on that for a second? So what do you mean by address the problem?
Yeah, so when I export using the API, usually each paper will be a single row, right? But when you have these big like Atlas collaborations in these physics papers, there's hundreds and hundreds of authors. It kind of overruns the structure and it breaks just that author list goes across probably 5 different rows in my Excel spreadsheet. Is there a way to limit the number of returned authors to, only 20 or something?
No, there's no way to do that. What you can do is to not return. I think people that try to tackle that in a different way, they maybe run queries where they don't return papers that have over, say, 500 authors or 200 authors, and you pull up your data like that. And then you do another run where you take only those few papers that have more than 500 authors. And then you have a separate process to maybe take only the top 20. But you wouldn't be able to do that only with the API. I understand what you're trying to do, yeah. So yeah, quick answer is no, there's no way to shorten that list. It's either or, but you can decide not to return publications that have more than a certain number of authors. Does that make sense?
Yes.
Yeah, okay, lovely. By the way, some reasons I've forgot how much more time do I have, Ines? Is it another half an hour, or am I already over time?
Yeah, you're over time, Michele.
I am over time, am I not?
Yes, you've gone for an hour.
Yeah. We've gone for an hour. Yeah, there's a huge amount of things to say. So I would say I would take a few questions now, and depending on the topic, I can then use the notebook to show other aspects of the DSL. Are there any other questions? Okay, I take it as a no. So I will just then take another 5 minutes, hoping people can do it, just to show another small thing. I think, yeah, returning results. I think we looked at returning specific fields, this whole notion about faceting. The other thing to keep in mind is that you can return up to a maximum of 1,000 records per query. So in this case, I'm returning 1,000. It will take a little bit longer. And I got my 1,000 records. If I say return, say 1,001, I will get an error. So there's a 1,000 maximum. So the way to work around this is to essentially say, skip the first 1,000 and go to the next, essentially round of 1,000 objects. So this operation is called pagination, and that's the way you would normally go through different pages of a result set up to 50,000. When you get up to 50,000, you will get another error saying, you can only take 50,000 results maximum for every single query. Yeah. So the way you work around that is simply by having different queries that slice your results in buckets that are smaller than 50,000. So for example, if you have your corpus defined by a couple of keywords, what you can do is, you would start by looking at how many results you have in total. So here I have 300,000, 240,000. And then you need to look for ways to essentially break this up into different chunks that are smaller than 50,000. So in this case, I'm faceting on years to begin with. Oh, sorry. I lost where I was. There you go. So I'm faceting on years, and as you can see here, no year has more than 50,000 results. So what can be done then is to simply set up a loop where you have one query per year, and for that year, you extract all the results using pagination. And by doing that, you can then extract all the full data set you are interested in. In some cases, you may have 1 year that has more than 50,000 results, so you probably have to find another way. You can maybe set, split it up by month, or even, depending on what you're trying to do, you can split up by a research organization or by subject area, and so on. Now, another feature we recently launched, and this is the last thing I'll be talking about, is called unnesting. I mean, if you have worked with API a bit, you probably have seen that in some cases, actually, let me try and do it right here. If I say search publications, actually, let's say I want to look at researchers linked to a specific query. Of course, I have more than one researcher per publication. So these researchers, they come through as a list of things. You know, there's more than one per publication. You know, if you're using this with Python, another programming language, you know, it's probably easy enough to look into this column, break out the data, and then do some other operation. If you don't want to do that, there's another useful feature which is called unnest. And unnest essentially breaks up that list for you directly using the API. So if I do this, I will get back a list of researchers. Well, it's still a list of publications, but I get one row per researcher. So what that means is that the same publication may be getting more than one row because the publication information is duplicated, and I'm kind of pivoting on the researcher information. So for those of you who use the API, for example, within Google Sheets, something like Google Sheets, where you know the tabular format is primary importance, unnesting is a very useful feature because you get data that you can act upon right away. You know, I can build a chart using this researcher's information, and so that's the unnest functionality. In this case here, for example, I'm unnesting categories. We have more than one category per publication normally. If you use a nest, you get a nice table back that has one row per category. And of course, I can combine a nesting operations, you know, as many as I want. The only thing to keep in mind is that this will produce an explosion of rows, because this is a bit like a cross join in SQL terms, meaning that, you know, you would have one row per single category, per single researcher, per single research organizations. And so the number of data you get back will be quite large. And I already feel I should stop here, unless people have specific topics you want me to look into. Otherwise, thanks so much for your attention, and sorry for running a bit over time. So do we have any more questions? I think there's a chat somewhere. I cannot see it. Can you see it, Ines, by any chance?
Sorry.
Okay, I can see the chat. It was the previous question from Eric, so we're good.
There's one question in the chat, but nothing else, nothing recent. Good.
So yeah, I think I hope it was all clear. This notebook is available online, so you can play with it. And any other question, you know, we're here. We're happy to help. So please do get in touch. Thanks again for watching.
Thank you. Bye.
All right. Bye.